This snippet of code is all about bringing in essential Python libraries for data analysis and visualization. NumPy is a go-to library for numerical operations in Python, known for its robust support of large, multi-dimensional arrays and matrices. Pandas, on the other hand, is a data manipulation powerhouse offering handy data structures like DataFrame, which streamline storing, tweaking, and scrutinizing data effortlessly. Matplotlib, pyplot serves as a plotting tool akin to MATLAB, enabling users to craft a variety of plots including line plots, histograms, scatter plots, and more. Seaborn, a Matplotlib-based data visualization library, ups the ante by providing a sleek interface for crafting captivating and informative statistical graphics. Plotly, Express steps in as a top-tier interface for producing interactive plots with the renowned Plotly, favored for data visualization scenarios that call for interactivity. By importing these libraries, you unlock the potential for data manipulation, analysis, and diverse visualization forms to extract insights from your data. With a wide array of functions and tools at your disposal, these libraries ensure efficient and effective data handling in Python. This script is designed to ingest a CSV file named Google 2006-1.2018-11, C that holds the historical stock prices of Google Alphabet Inc., and then import the data into a Pandas data frame. By setting the indexAllDate parameter, it designates the date column as the data frame's index, streamlining the handling of time series information. Moreover, the parseDatesDate parameter assists Pandas in converting the date column entries into datetime objects, simplifying the manipulation and examination of time-related data. Subsequently, the head method is employed to exhibit the initial rows of the data frame, offering a glimpse of the data arrangement and details. This script allows the transformation of historical stock price details into a structured layout, facilitating in-depth analysis and visualization employing the robust functionalities delivered by the Pandas library in Python. In this script, a CSV file titled 2006-1.2018-11 CSV is imported into a Pandas data frame, with the date column designated as the data frame index. Moreover, the date column is converted into date format for easier handling. Assigning the date column as the index and converting it into date format enables seamless manipulation of time series data within Pandas. This functionality facilitates a multitude of operations on the data, including plotting time series information, computing rolling averages, and conducting date-oriented aggregations. In this code snippet, a CSV file titled Kamsen 2006-1.2018-11 CSV is imported into a Pandas data frame named Amazon. The data frame's index is then configured to be the date column, with the date values being converted to datetime objects for better analysis. Next, the head method is employed to reveal the initial records of the Amazon data frame. This code is essential for converting the CSV file data into a structured format data frame that eases data manipulation and analysis. By designating the date column as the index and converting date values, it enables efficient execution of diverse time series tasks on the dataset. This snippet of code is designed to retrieve data from a CSV file denominated M2006-1.2018-11, say and store it in a Pandas data frame under the name item. By specifying indexAllDate, the code assigns the date column as the primary index for the data frame. The parseDatesDate parameter is utilized to ensure that Pandas accurately interprets the date column values as dates. Once the data is imported into the data frame, the head method is employed to exhibit the initial rows of the item data frame. Employing this code is essential for efficiently converting and scrutinizing the data from the CSV file into a structured format suitable for adept data analysis, manipulation, and visualization using the Pandas library. The snippet you shared, Google, describe, seems to be calling a method on an object named Google. However, without additional context or insights into how the described method functions within a Google object, it's challenging to precisely determine its purpose. In general, the described method is commonly employed to fetch details or metadata related to the Google object or execute specific actions specific to the object. It usually serves to showcase information about the object, its attributes, functions, or provide a rundown of its capabilities. In order to grasp the functionality and rationale behind this code snippet, Delving into the inner workings of the describe method within the Google object is necessary, or having more clarity on the intent behind utilizing the describe method in this particular scenario would be beneficial. The phrase Google columns doesn't hold a defined significance within Python. It doesn't seem to be a standard Python function or method. It appears more likely to pertain to a customized module or library, possibly within a Pandas data frame or when interacting with a Google Sheets API client. To gain a clear understanding of its functionality, examining both its contextual usage and the associated library module documentation is essential. Typically, this code snippet is employed to retrieve column details or carry out operations related to columns in a data structure like a data frame, spreadsheet, or a similar entity. Familiarity with the libraries and modules incorporated in the code becomes pivotal in accurately deciphering the intention behind this syntax. The code snippet Google info seems to be invoking the info function on an object referred to as Google. To grasp its precise function, understanding the particular scenario in which this code is employed is essential. Nonetheless, generally speaking, calling the info function on a Google object indicates that the object holds an info method that likely furnishes relevant information or data pertaining to the object. It's common practice to utilize such methods for fetching or exhibiting details about an object, its attributes, or its status. This can prove valuable for tasks like troubleshooting, recording, or showcasing critical specifics about an object in a program. In essence, this piece of code probably fetches some form of information linked to the Google object, though the exact nature of this information hinges on how the info method is implemented within the Google object. In this code snippet, each value in a column of a Pandas data frame stored from Google undergoes scrutiny for missing or null values, also known as null values. The subsequent utilization of the sum function facilitates the tallying of missing values within each column. By leveraging the ISNA method in Pandas, a data frame is generated portraying true and false values. Here, true signifies a missing or null value, while false signifies the presence of a value. Through the summation of these Boolean values, a comprehensive count of missing values within each column is ascertained. Vigilance towards missing values within a dataset holds paramount importance, as their presence can significantly impact the accuracy and efficacy of data analysis and machine learning algorithms. This code snippet proves invaluable in swiftly pinpointing and comprehending the scope of missing data within the Google data frame. The command Microsoft describe does not carry a universal significance in Python or other widely used programming languages. It appears more like a placeholder or a theoretical function. Nonetheless, in practical scenarios, describe could serve as a method or function utilized to furnish information, particulars, or attributes about a particular object, class, module, or data structure linked to the variable Microsoft. If we were to devise a method akin to Microsoft describe to portray an object, it would probably be tailored to showcase pertinent information, features, or qualities of the Microsoft object. This encompasses information like its dimensions, configuration, hue, contents, or any other relevant details that facilitate a better comprehension of the object. Generally speaking, such a method proves beneficial for debugging, testing, or merely offering an overview of an object or class without divulging its internal workings or necessitating direct access to the object's characteristics. Hence, the capacity to elucidate an object utilizing a personalized method like describe can enrich the readability, manageability, and practicability of the code, particularly within extensive code bases where swiftly grasping complex objects holds significance. The function Microsoft info is considered invalid in Python and various programming languages. Nevertheless, hypothetically speaking, if we were to establish an info function inside a Microsoft class in Python, its primary purpose would involve presenting details about said class or object. This function would reveal specifics like the version or pertinent properties associated with the Microsoft class. It is a customary practice in software development to incorporate informative functions, such as info, to aid developers in comprehending the attributes and functions of a given class or object better. Such practices contribute to enhancing code clarity, documentation, and streamlining the debugging process. This piece of code is commonly utilized in Python alongside the Pandas library for data manipulation. In essence, Microsoft denotes a Pandas data frame or series that likely contains unspecified or not available entries. By utilizing the ISNA method, the script locates missing values within the data frame or series. It generates a Boolean mask that flags true for missing values and false for the opposite. Following that, the sum function is applied to the ISNA outcome to calculate the quantity of missing values in each column if Microsoft is a data frame, or in the whole series if Microsoft is a series. The output will reveal the total sum of true values, which is tacitly treated as 1 within each data frame column or the series. This code proves invaluable for swiftly pinpointing the quantity of missing values in a dataset, a pivotal step for both data analysis and data processing endeavors. Understanding the number of missing values enables us to strategize on addressing or rectifying these gaps to prime the data for subsequent analysis or modeling purposes. The syntax Amazon info isn't typical in Python and requires defining Amazon in the code to function correctly. The code seems to be calling the method info on an object or variable labeled as Amazon. To grasp the code's purpose, we must have insights into the Amazon object's definition and the implementation of the info method. Without this context, offering a precise explanation is challenging. In a broader context, the snippet may be a segment of a larger program where Amazon represents an object storing Amazon product details. The info method likely serves to retrieve or showcase information about these products. It could facilitate tasks like fetching data from Amazon's database, exhibiting product details to users, or executing operations associated with Amazon products. When you spot the code Amazon describe, it most likely signals the invocation of a function or method dubbed describe from a designated object or instance known as Amazon. Unlike inbuilt functions, the described function in Python is typically crafted by users as a method within a class framework. This method functions to furnish structured insights into the Amazon object, shedding light on its distinctive features, properties, or behavior. Employing code such as Amazon describe proves advantageous in fetching tailored details or specifics regarding the Amazon object, aiding in tasks like debugging, logging, or gaining deeper insights into the object's runtime status. It elevates code clarity, streamlines the management of intricate objects, and introduces a standardized approach to presenting object-related information. Utilizing the code Amazon columns allows you to fetch the header labels in a data frame that portrays the dataset named Amazon. The utilization of the columns attribute within the Pandas library provides a means to retrieve and exhibit the column titles within the data frame. This data proves beneficial in comprehending the dataset's layout and in engaging with particular columns for diverse tasks like analysis, sifting, or data manipulation. Extracting the column names enables you to pinpoint and handle individual columns for subsequent processing or analysis within the dataset. This snippet of code comes in handy for detecting missing or non values within a data frame. For example, an Amazon dataset, the ISNA function is applied to the data frame, yielding a new data frame of the same dimensions. It showcases booleans indicating the presence or absence of each element. True stands for missing values, while false represents non-missing ones. Subsequently, the sum function is employed to tally the Boolean values across columns, furnishing a comprehensive count of missing entries within each column of the data frame. This code proves invaluable in swiftly pinpointing the quantity of missing values residing in each column of the Amazon dataset. Such insights play a pivotal role in the realm of data preparation and examination, aiding us in devising strategies to address missing data before advancing to subsequent computations or analyses. The GIM describe function in Python is commonly utilized with the Watson library to gather insights or a rundown about a particular asset, like a machine learning model, a service, or any object linked to Watson services. By invoking GIM describe, it pulls in the specifics and metadata tied to the designated asset, which can be leveraged for diverse tasks such as tracking the status, setup, or performance of the asset. This data can come in handy for investigating issues, fine-tuning, or gaining a general overview of the asset's condition at any given point. In essence, the goal of GIM described is to furnish comprehensive details regarding a distinct resource or service, aiding developers and users in grasping and handling their Watson assets more effectively. This snippet of code seems to be aiming to access a property or method titled columns on an object labeled as item. Without more context, the specific purpose remains unclear, but it appears to align with common practices seen in data manipulation frameworks like Pandas and Python. Within the Pandas library, the columns attribute serves to fetch the column headings from a data frame or series. It comes in handy for retrieving and referencing the columns during data analysis, manipulation, or other data-related operations. In essence, this code snippet likely plays a crucial role in handling tasks related to data analysis and manipulation. Grasping and managing columns within a dataset stand as a foundational element in navigating data within Pandas and Aiken libraries. This snippet of code serves the purpose of detecting absent or not a number not an elements within a Pandas data frame named item. By utilizing the ISNA method, it produces a Boolean data frame mirroring the original one wherein each item is marked as true if it represents a non-value, and false if not. Subsequently, the sum function is employed to compute the total count of true values indicating non-items within each column of the data frame. This procedure provides insights into the quantity of missing values present in individual columns of the item data frame. Such code proves to be valuable in tasks related to data preparation and quality assurance by pinpointing any missing values within the dataset. Addressing missing data is crucial as it can impact the validity of subsequent analyses and result interpretations. Detecting and handling missing data stands as a vital preliminary phase prior to engaging in any data scrutinization or modeling activities. This snippet of code serves to eliminate any rows in a data frame that possess missing values. Commonly known as nonnies, the dropna function is a handy tool from Pandas tailored for discarding rows with non-values. By setting in place true, you can directly tweak the original data frame sans the requirement of reassigning the outcome to a fresh variable. As a result, the data frame will undergo alterations on the spot, rendering the adjustments permanent. We employ this piece of code to refine our data by straining out any absent values, as they have the potential to disrupt smooth data analysis or machine learning algorithms. The eradication of these missing values guarantees the integrity and precision of the dataset for subsequent analysis or modeling purposes. This snippet of code serves the purpose of tallying absent values not and or none within a specific column labeled item in a Pandas data frame. Here's how it functions. The column item is a part of the Pandas data frame. By using the ISNA method, each element in the item column is inspected to identify any missing data. It generates a Boolean mask matching the original data frame's structure, where true indicates missing values and false denotes otherwise. Subsequently, the sum function totals up the count of true values within the Boolean mask, representing the quantity of missing values within the item column. Employing this code enables us to swiftly assess and quantify the extent of absent data in the item column for tasks like data analysis or preparation. Understanding the quantity of missing values in a dataset is crucial for activities such as data refinement and imputation, as incomplete data can notably impact the accuracy and credibility of statistical evaluations and machine learning algorithms. This piece of code leverages the Plotly Express library to create a histogram illustrating the distribution of close prices within a dataset named Google. In the setup, the X parameter denotes the data presented on the x-axis, featuring close. Opting for marginal set to box results in a combined display of a box plot alongside the histogram. The newBins parameter controls the division of data into bins. With title, a title is assigned to the plot. To fine-tune the plot layout, the update layout method is utilized, incorporating bar gap to define the gap between bars in the histogram. Conclusively, Fig Show is implemented to showcase the histogram with the specified adjustments. This code expedites the creation of a histogram integrated with box plot details and personalized attributes such as title and bar gap preferences. Such visual aids are instrumental in comprehending the distribution of closed prices, facilitating data interpretation and informed decision-making. Utilizing the Plotly library in Python, this script constructs a histogram overlaid with a box plot, illustrating data from the open column within the Google data frame. Let's break down its functionality. 1. The script generates a histogram showcasing values from the open column of the Google data frame. 2. It supplements the histogram with a box plot overlay, offering a visual summary including median, quartiles, and potential outliers. 3. The histogram color is customized to read using the color districtsequence parameter. 4. The plot title is assigned as distribution of open. 5. Adjustments to the plot layout involve setting the gap between histogram bars to 0, 1 through the bar gap parameter, 6. Lastly, the plot is exhibited using the show method. This script proves to be beneficial for illustrating the distribution and central tendencies of open prices within the Google stock dataset. The histogram aids in comprehending data dispersion, while the box plot assists in outlier identification and enhancing understanding of the overall distribution. Employing visualizations like these is paramount for exploratory data analysis, facilitating valuable insights extraction. Utilizing the Plotly library, this script generates a scatter plot for comparing stock prices, with the open price on the x-axis and the close price on the y-axis. The markers are slightly transparent at 80 opacity for a subtle effect. The plot is titled Open versus Close. Each data point is depicted as a marker. Resized to a marker size of 5 for clarity, this code is valuable for visually exploring the relationship between stock opening and closing prices, facilitating the detection of trends and correlations. The adjustments in marker opacity and size enhance the visual appeal and informational value of the plot. Plotly, a sought-after visualization tool, enriches Python data analysis with interactive and high-resolution graphics, making it a go-to choice for diverse data visualization needs. It seems like this code is aiming to utilize the core function on a variable labeled Google to determine the correlation among values within a dataset. Typically, the core function is employed to calculate the correlation between distinct columns of data in either a data frame or a series. This function computes the correlation coefficient, a numerical value ranging from 1 to 1 that signifies the magnitude and orientation of a linear relationship between two variables. Correlation holds significance in the realms of statistics and data analysis as it aids in comprehending the connection between diverse variables in a dataset. It serves the purpose of uncovering patterns, pinpointing dependencies, and facilitating predictions based on the available data. With the Google core method, we can promptly evaluate the degree of association between various columns in our dataset, thereby offering valuable insights for subsequent analysis or decision-making endeavors. The provided code snippet employs the slicing technique of Pandas data frame to isolate a specific set of rows for subsequent data plotting. It appears to be plotting the Google stock data from the years 2008 to 2018. Subsequently, the plot function is applied to create individual subplots for each attribute, incorporating customized visualization options such as subplots arrangement and figure size. Following this, a title is included in the visualization, after which Plt. Show is called to display the plot. This code serves as a practical tool for visualizing targeted data ranges across a timeline. In the instance provided, it focuses on illustrating the stock attributes of Google within the 2008 to 2018 timeframe. Leveraging this visualization technique aids in uncovering trends, identifying patterns, and recognizing relationships inherent in the data, thereby facilitating the extraction of valuable insights and enabling well-informed decision-making. In this snippet of code, Pandas functionality is utilized to generate a series of subplots showcasing various attributes of Microsoft stock spanning from 2008 to 2018. The code filters the data for the specified time frame using slicing syntax 2008-2018 and proceeds to create separate subplots for each stock attribute. The figure's dimensions are determined by the fixed size parameter. Following the plot creation, the title of the visualization is set as Microsoft stock attributes from 2008 to 2018. Employing this code allows us to visually explore Microsoft stock attributes throughout the designated period, enabling us to analyze the stock's performance and behavior. Breaking down the attributes into distinct subplots facilitates a comparative analysis of different facets of the stock's performance across time. Through this graphical representation, trends, patterns, and correlations within the data can be more effectively observed and interpreted. Below is a code snippet that illustrates the data pertaining to Amazon stock attributes between the years 2008 and 2018. The snippet employs slice notation to extract data within the 2008-2018 range and then presents it as subplots with a customized figure size. The plot's title is set using the Plt. Title function, and the resulting plot is displayed using Plt. Show. Analyzing and visualizing Amazon stock attributes data during this period is essential. By depicting the data in subplots, we can compare various attributes such as stock price, volume, and more throughout the years to glean valuable insights into Amazon's stock market performance. This visual representation aids in identifying trends, patterns, and correlations within the data, ultimately facilitating informed decision-making in investment strategies or financial analysis. Utilizing the Pandas library, this code excerpt filters stock data from 2008 to 2018 and generates multiple subplots to exhibit various stock attributes across this timeframe. The plot function visually represents the data, incorporating the subplot's true parameter to create distinct plots for each attribute, and the fixization 12 parameter to determine the plot's overall dimensions. Adding a descriptive label using plot title gives the plot a clear identity, denoting that it showcases stock attributes spanning 2008 to 2018. To present the plot to the user, plot show is employed. By employing this script, we visualize stock data within a specified time frame, gathering insights into the evolution of diverse stock attributes throughout the given duration. Visualization serves as a tool to detect trends, patterns, and irregularities, facilitating decision-making processes pertaining to stock analysis and investment. The code excerpt below demonstrates the plotting of the highest stock prices of 4 prominent companies: Google, Microsoft, Amazon, and using the Matplotlib library. 1. The script fetches the high stock prices for each company from their corresponding datasets: Google, Microsoft, Amazon. 2. By employing the plot method, a line graph depicting the high stock prices for each enterprise is generated. 3. To distinguish between the stock prices of individual companies, a legend is incorporated into the plot. 4. Finally, the plot is exhibited utilizing the plot show function. This code empowers us to visually assess and compare the high stock prices of multiple companies on a unified graph, facilitating the identification of trends and patterns. Visual representations such as this play a crucial role in data analysis and decision-making across various domains such as finance, economics, and business. Below is a guide on how the script operates, generating a visual representation of Microsoft stock's high prices, expanding mean and expanding standard deviation over time. Initially, the code computes the expanding mean and standard deviation of Microsoft's high prices. The expanding mean encompasses all prior data points leading up to the current one and continuously adjusts as new data streams in. Likewise, the expanding standard deviation considers all historical data points and adapts as fresh data gets incorporated. Subsequently, the script executes the command Microsoft high plot to portray Microsoft's high prices graphically. Concurrently, Microsoft mean plot and Microsoft's plot illustrate the expanding mean and expanding standard deviation on the same graph, showcasing the high prices. To differentiate between the high prices, expanding mean, and expanding standard deviation, the plot legentic expanding mean, expanding standard deviation function is implemented, creating a legend for the plot. The plot is titled Microsoft using plot table Microsoft, setting a descriptive header. Finally, plot show renders the graphical representation displaying Microsoft stock's high prices, expanding mean, and expanding standard deviation. This script proves invaluable for observing the fluctuation of Microsoft stock's high prices in conjunction with their expanding mean and standard deviation, aiding in the analysis of trends, volatility, and overall performance of the stock. The following script conducts an analysis on the high column data of Google stock. It first computes the expanding mean and standard deviation using the expanding function. Next, it generates a graphical representation by plotting the high column data, the expanding mean, and standard deviation on a single graph utilizing the plot method. To enhance clarity, the script includes appropriate legends and a title for the plot. The final step involves displaying the plot with plot show. This script is effective for observing how the high values of Google stock change over time relative to their expanding mean and standard deviation. It aids in discerning patterns, fluctuations, and the distribution of stock prices over time. By visualizing the information in this manner, one can gain insights into data patterns and potential anomalies within the dataset. This script is designed to compute the cumulative mean and standard deviation of the high column within a dataset named DIM. The cumulative mean represents the average of all previous values in the dataset up to the current point, while the cumulative standard deviation illustrates the variability of all values up to that point. Following the calculation of the cumulative mean and standard deviation, the script generates a visual representation plotting the high column alongside the cumulative mean and standard deviation from the dataset. This graphical presentation aids in grasping the fluctuations in NASDAQ high values over time, offering insights into how they relate to the cumulative mean and standard deviation. The utilization of this script proves beneficial in observing trends and deviations in NASDAQ high values across time, facilitating a more straightforward analysis and interpretation of the dataset. The provided script computes the expanding mean and standard deviation for the high column in the Amazon dataset. Here, Amazon is presumed to represent the dataset. These metrics are continuously calculated for each row, including all preceding rows in the dataset up to that specific point. Subsequently, a plot is generated that overlays the high column of the Amazon dataset with its expanding mean and standard deviation. This visual representation aids in grasping the trend and fluctuations in the high prices of Amazon stock across time. Employing the expanding mean and standard deviation in this script helps in smoothing out fluctuations present in the data, allowing for a clearer observation of long-term patterns and fluctuations. Such analysis proves valuable in identifying trends or irregularities in the dataset, enabling well-informed decisions based on past performance. In this code snippet, the expanding mean and expanding standard deviation for the close prices of Google stock are computed and visualized. Let's break down the code process step by step. 1. Initially, the expanding mean of the close prices is determined by employing the expanding method followed by the mean method. 2. Next, the expanding standard deviation of the close prices is computed with the expanding method followed by the steady method. 3. Subsequently, a plot of the high prices of Google stock is generated using Google High Plot. 4. The calculated expanding mean is plotted using Google Mean Plot. 5. The expanding standard deviation is plotted using Google-list plot. 6. A legend indicating the corresponding data for each line is added to the plot. 7. The plot is titled as Google. 8. Eventually, the plot is showcased with 3 distinct lines: high prices, expanding mean, and expanding standard deviation. This code segment is utilized to visually represent the high prices alongside the expanding mean and expanding standard deviation of the close prices for Google stock. This visualization aids in grasping the trends and variations in stock prices over time. This snippet of code brings in the RepairEms class from the PyLab module and imports the complete stats models. API module. The RepairEms class in PyLab is handy for controlling default settings like figure size, line thickness, colors, and font sizes when creating plots in Python. On the other hand, statsmodels is a powerful Python module that offers a variety of classes and functions for statistical testing and estimation. By leveraging RepairEms, we can personalize the look of our plots and visualizations, while tapping into the capabilities of statsmodels to access numerous statistical models and tests that are frequently employed in data analysis and modeling. This snippet of code allows for the visualization of the seasonal breakdown of a time series dataset that showcases the daily peak values of Google's stock prices. By setting the RepairEms figure size to 11:9, the code establishes the size of the displayed figure for plotting the seasonal decomposition. Utilizing the seasonal decompose function from the statsmodels library, the time series data gets decomposed into trend, seasonal effects, and residuals. Specifically, the code feeds the function with the daily high prices of Google stock and a frequency of 360, signifying annual seasonality within the dataset. Following the decomposition, the code generates a graphical representation of the broken down elements through the plot function of the decomposed Google volume object. Subsequently, bolt_show is employed to exhibit the plot visually. This code proves handy for visualizing both the trend and seasonal characteristics within the time series dataset, aiding in the comprehension of underlying patterns and enhancing predictive capacities or analytical insights grounded on the decomposed constituents. The act of visualizing seasonal breakdowns holds significance in time series analysis as it helps in pinpointing trends, patterns, and irregularities within the data. In preparation for plotting a seasonal decomposition chart showcasing the high values of Microsoft stock prices, the following code snippet is employed to resize the figure. Here's a breakdown of the code's functions. 1. Setting the dimensions of the plot to 11:9 units using RepairEms figure. Fig size carries out the figure size adjustment for plotting purposes, offering a width of 11 units and a height of 9 units. 2. Utilizing the seasonal decompose function from the stats models library Seasonal decomposers of TIE for 360 separates the trend, seasonal, and residual constituents of the time series information. This process is applied to the high values of Microsoft stock prices with a frequency of 360, signifying yearly partitioning. 3. Creating the seasonal decomposition plot based on the preceding decomposition is done using the line figure decompose Microsoft volume. Plot. 4. To exhibit the plot, show is utilized. Adjusting the figure size before producing plots proves beneficial while leveraging visualization tools to ensure the clarity and aesthetic appeal of the visuals. The seasonal decomposition plot delves into the fundamental patterns in the time series data by disassembling it into distinct components. This breakdown aids in grasping the trend, seasonality, and irregular aspects embedded within the data. In the script provided, adjustments are made to the figure size for displaying plots by setting params figure. Fig size. Next, the script employs the seasonal decompose function from the stats models module to decompose the time series data found in the high column of the adding data frame. The decomposition frequency is established at 360, indicating an annual seasonality. Subsequently, a plot illustrating the decomposed elements trend, seasonal, and residual of the high prices of item stock is generated using the plot method associated with the results of the seasonal decomposition. To conclude, the plot is exhibited using show. This methodology aids in visualizing the various components of the time series data, encompassing trend, seasonality, and residuals. By unraveling such patterns, analysts can gain deeper insights into the data, enabling them to make well-informed decisions in the realms of time series analysis and forecasting. Below is the code snippet that illustrates the seasonal breakdown of the historical high stock prices of Amazon initially. The code sets the dimensions of the figure for showcasing the plot. It proceeds by computing the seasonal decomposition of Amazon's high stock prices through the utilization of the seasonal decompose function from the stats models. Library, with a frequency parameter set at 360, this assumption is made based on each data point representing a day, resulting in the data being annual. Subsequently, the plot function is employed to visually display the separated elements trend, seasonal, and residual of Amazon stock prices. To conclude, show function is called upon to exhibit the plot visually. This piece of code proves to be advantageous for scrutinizing and illustrating the trends, seasonal variations, and leftover elements in Amazon's high stock prices over the timeline. It facilitates the comprehension of data patterns and fluctuations, which can be deemed crucial for investment evaluations or further exploration of the dataset. In this script, the figure's dimensions for showcasing a seasonal decomposition plot are being customized. The line params figure, fig size 11:9 establishes the figure's width as 11 inches and height as 9 inches. The primary goal of this piece of code is to conduct seasonal decomposition on the closing prices of Google stock Google close using the seasonal decompose function provided by the stats models library. By setting the front 360 parameter, the code indicates that the data has an annual frequency, implying that the decomposition revolves around a yearly cycle. Subsequent to the seasonal decomposition process, the script plots the decomposed elements trend, seasonal, and residual using the plot function and then showcases the plot via show. By adjusting the figure size, the clarity and readability of the seasonal decomposition plot are enhanced, aiding in a better comprehension of the data's decomposed elements. Optimal figure sizing contributes to improved visualization and analysis of the seasonal trends portrayed in the closing prices of the stock. The provided code snippet adjusts the figure size before displaying a seasonal decomposition of a time series dataset containing the closing prices of Microsoft stock. This decomposition is executed through the seasonal decompose function available in the stats models library, which segments the time series into trend, seasonal, and residual parts. The script sets the plot's dimensions using params figure, fig size, determining how the plot will appear visually. This setup ensures the plot is shown in the specified size and proportions. For the seasonal decomposition, a frequency of 360 is designated, representing an annual seasonal cycle within the data. The decomposed segments are then graphed using the plot function, and the resulting graph is exhibited using PULT. Show. In essence, this code snippet serves the purpose of visually examining and interpreting the seasonal trends within the closing prices of Microsoft stock. Through breaking down the time series into its constituent elements, it aids in comprehending the underlying trend, seasonal variations, and residual changes observed in the dataset across time. The following snippet of code is utilized to create a graphical representation of the decomposed time series of Amazon stock's closing prices. It commences by defining the size of the figure for the plot, followed by applying the seasonal decomposition function from the stats-modules library. This function dissects the closing prices into distinct elements including trend, seasonality, and residual components. The frequency parameter is specified as 360 to signify a yearly single seasonal cycle within the data. Subsequently, a plot is produced to visualize the decomposition. Employing this code aids in unraveling the intrinsic patterns and tendencies present in the time series data by segmenting the various components. This process facilitates the identification of seasonal fluctuations, general trends, and irregularities in the data for subsequent examination and predictive analysis. In the given code snippet, the seasonal decompose function from the stats-modules library is applied to deconstruct a time series dataset representing M stock prices into its trend, seasonality, and residual constituents. Here's a breakdown of how it operates. 1. By setting reference figure, fig size 11:9, the default dimensions for matplotlib plots are established to be 11 inches wide and 9 inches tall. 2. The line decomposed volume sum, seasonal decomposum close. Front 360 dissects the time series data encapsulating the closing prices of M stocks. Specifying front 360 indicates a seasonal cycle of 360 time units in this scenario, approximately a year spanning 360 trading days. Subsequently, the function dissects the time series into trend, seasonal, and residual portions. 3. Generating a graphical representation illustrating the decomposed elements trend, seasonality, and residual and storing it in the figure variable is accomplished through the statement figure decomposed volume. Plot. 4. The plot is exhibited on the screen through PULT. Show. Employing this code allows us to visually analyze the distinct elements of a time series dataset, such as M stock prices, aiding in the examination and comprehension of patterns contained within the data. Unpacking a time series can furnish valuable insights into fundamental trends and periodic fluctuations, proving beneficial for predictive analysis and facilitating informed decision-making grounded in the dataset. The snippet of code provided loads a CSV file that contains historical stock price records of Amazon spanning from January 1, 2006 to January 1, 2018 into a Pandas data frame. It proceeds to arrange the information by sorting it in ascending order according to the date column and then exhibits the initial entries of the ordered data frame. Parsing and handling information from a CSV document is a routine duty in various data analysis and data science endeavors. By importing the information into a data frame and arranging it, we can scrutinize the data more efficiently, create visual representations, or draw valuable conclusions from the dataset. The chronological organization of the data by date in this script guarantees that the information is structured in a time-based sequence, a critical aspect for time series analysis and visualization purposes. The following code segment serves to display the closing stock prices of Amazon across a specific time frame, providing insights into stock trends. Here's a breakdown of the code's functionality. 1. Firstly, it imports essential libraries, namely matplotlib and cburn. 2. It configures the plot style as dark grid through cburn settings. 3. It generates a plot window sized at 15:9 units using matplotlib. 4. The plot showcases the closing price details sorted from a data frame denoted as data composition. 5. It enhances readability by adjusting context to align with the data index and date values. 6. Noteworthy labeling, including title, label, and syllable, is integrated into the plot for clarity. 7. Ultimately, the executed code presents the plot for visualization purposes. Leveraging such visualization aids in comprehending data effortlessly, uncovering intricate patterns that might elude a cursory data inspection. This graphical representation distinctly illustrates Amazon's stock price fluctuations, facilitating sound decision-making in trading or investment endeavors. In this code excerpt, data is being extracted from a CSV file labeled Google 2006 2018 and stored in a Pandas data frame named data Google. Subsequently, the data frame is organized in ascending order based on the date column. By employing this script, financial information regarding Google's stock is being imported from the CSV file and transformed into a structured form data frame that facilitates easy manipulation and examination through Python. The chronological sorting of the data allows for a coherent analysis, which is beneficial for tasks like time series analysis or visualizing time-related data. The code below utilizes matplotlib and cburn libraries to create a line plot that illustrates the stock price data of Google. By employing JSON's set-style dark grid, the plot adopts a sleek appearance with a dark grid background from cburn, enhancing its visual appeal. To ensure optimal visualization, default figure size of 15:9 is utilized to establish a new figure sized at 15:9 inches. Plot Google close is employed to plot the close price data extracted from the data frame. Data Google for improved readability. Text range 0, data Google, shape 0, 500, data Google date, plus 500. Rotation 45 configures the x-axis ticks and labels to display every 500 data points, showcasing corresponding dates with a 45-degree rotation. Titles, labels, and fonts are set as follows. Title Google stock price, font size 18, font weight bold, global date, font size 18, and syllables price cost, font size 18. The visualization is presented using show, offering a comprehensive overview of the Google stock price data in a visually appealing manner. Such visualizations play a crucial role in deciphering and analyzing intricate datasets effectively by adjusting figure size, style, title, labels, and tick marks to maximize readability and data presentation quality. The following script imports data from a CSV file labeled im2006 2018 into a Pandas data frame. It proceeds to arrange the data in chronological order based on the date column. Eventually, it showcases the initial rows of the ordered data frame utilizing the head function. Utilizing this script is crucial for handling and structuring information emanating from a CSV file illustrating stock market figures during a specific time frame. Ordering the records by date guarantees a sequential arrangement, which proves pivotal for analyses and visual representations reliant on time-based patterns. Reviewing the initial rows enables us to confirm the accurate upload of data and its alignment with the expected layout. In this snippet of code, any rows in the data frame labeled as datatim that include any missing values not in or being removed. The addition of the parameter in playthrough facilitates the direct implementation of these modifications to the initial data frame, saving the hassle of generating a new one. Getting rid of rows containing non-values guarantees that the dataset remains tidy and devoid of inaccuracies, preventing potential errors in subsequent analysis or modeling endeavors. This method is vital for upholding data consistency and guaranteeing the precision of our analytical outcomes. Utilizing the matplotlib and cburn libraries, this code snippet generates a line plot illustrating stock prices. Here's a breakdown of its functionality. 1. By invoking SIN's set-style dark grid, the plot takes on a sleek appearance with a dark grid background via the cburn library. 2. The line plot figure fixes in 15:9 initiates a new plot figure sized at 15:9 inches. 3. Through plot out its glows, the code renders a line graph depicting the closing prices of stock based on the input data. 4. For enhanced readability, plot text range 0, datatim, shape 0, 500, datatim date, plus 500. Rotation 45 configures the x-axis ticks to show up every 500 data points, labeled with corresponding dates from the date column and rotated by 45 degrees. 5. The line plot title stock price, font size 18, font weight bold assigns a title of stock price to the plot with specified font size and weight. 6. Plot global date, font size 18 titles the x-axis as date, formatted with the designated font size. 7. Designated as plot syllables price cost, font size 18, the code labels the x-axis as close price cost using the selected font size. 8. Lastly, invoking plot show brings the plot to the display for viewing. This code proves invaluable in presenting stock price data in an organized and insightful manner. Facilitating thorough analysis and comprehension, visual representation aids in pinpointing trends, patterns, and anomalies within the data that may elude detection through mere numerical examination or tabular review, offering an easily interpretable and communicable snapshot. The primary function of this script entails fetching historical data for Microsoft stock prices from a CSV file, arranging the data based on the date column, and showcasing the initial rows of the organized data. Initially, the program imports the data from the files 2006-1 into 2018-1 CV, housing Microsoft's historical stock prices utilizing the PD reads function. Subsequently, the information gets organized by the date column in ascending sequence through the data Microsoft sort value state operation. Lastly, it exhibits the first few rows of the restructured data frame by executing data Microsoft head. This code bears significance as it aids in structuring and scrutinizing time series data, particularly the past stock prices of Microsoft, facilitating a more straightforward interpretation and extraction of key insights from the dataset. The provided code snippet employs Matplotlib, Pyplot, and Seaborn libraries to generate and exhibit a line plot illustrating Microsoft's stock price data. Let's delve into the breakdown of its functionality. Firstly, it adjusts the plot's aesthetics by setting the Seaborn style to dark grid. Next, it establishes a figure with defined dimensions 15 inches in width and 9 inches in height. The code then proceeds to plot the closing prices of Microsoft stock sorted from a data frame named Data Microsoft. It further customizes the axis ticks, ensuring every 500th tick displays correlated dates. With text rotation for enhanced readability, the plot receives a title of Microsoft stock price styled with a designated font size and weight. The x-axis is labeled as date, while the y-axis as close price cost, each with specified font sizes. Conclusively, the plot is showcased, culminating the execution flow. This code proves vital in portraying stock price data as a time series. Unraveling trends, patterns, and irregularities, visualization acts as a potent asset in data scrutiny and delivery, paving the way for comprehensive comprehension and analysis of data. In this instance, it aids in mapping out the evolution of Microsoft stock prices across time. The snippet of code extracts the close column from a data frame titled Data Amazon and saves it as a new data frame named Pre-Amazon. Subsequently, the info method is invoked on the Pre-Amazon data frame to present details about the data frame, including the data types of each column and the number of non-null values. Leveraging this code can offer a swift way to review specifics of a particular portion of data within a data frame, like comprehending the data types and the existence of missing values in the close column of the Data Amazon data frame. This process can facilitate data exploration and validation, empowering insightful decisions for subsequent data processing and analysis. In this code snippet, the min-max seller from the scikit-learn library is utilized to normalize the close column within the dataset named Pre-Amazon. The min-max seller function is employed to standardize and adjust each feature independently, ensuring it falls within a predefined range, typically set between 1 and 1. This approach proves valuable, notably when dealing with features exhibiting varying value scales. By normalizing the data through this method, the effectiveness and consistency of machine learning models are enhanced, particularly those dependent on distance computations such as key nearest neighbors or neural networks. Through fitting the seller to the close column in the Pre-Amazon dataset, the original values undergo a conversion to fit within this 1-to-1 range. The process involves reshaping the data to a singular feature format using values, reshape 1 before feeding it into the fit transform function of the min-max seller. Overall, this code segment readies the close column in the Pre-Amazon dataset for machine learning assignments by standardizing its values to a specified range. This adjustment aims to optimize the performance and precision of models trained on this dataset. The function provided is termed split data and serves to divide data efficiently for training and testing a machine learning model. It takes two arguments stock transformed into a numpy array and a window size denoted by the lookback parameter. Firstly, the function converts the stock data into a numpy array to facilitate handling. Subsequently, an empty list named data is instantiated to house the divided data. The code then proceeds to traverse the data array, creating sequences of length lookback. These sequences form the basis for the input features and output labels. Upon segmenting the data array into training and testing sets, it further delineates the input features X and output labels Y for both sets. The function concludes by returning these divided datasets as a list comprising heattrain, A-train, ctest, and heatest. This code is particularly valuable for preprocessing time series data before introducing it to a machine learning model. It plays a pivotal role in segmenting data into distinct input features and output labels to enhance the model training and testing phases. Through this division process, the model avoids simply memorizing the data, instead learning to generalize effectively from it. This piece of code is designed to format data ahead of training a machine learning model with a time series dataset. Commonly utilized for analyzing stock prices, initially, the code establishes a variable called lookback, denoting the length of the sequence utilized to forecast the subsequent data point. The split data function, which segments the pre-Amazon dataset, is employed to generate input sequences heattrain and heatest and their corresponding outputs or targets heattrain and heatest. Input sequences are constructed by selecting a series of lookback consecutive data points as attributes, while target values correspond to the subsequent data point following each sequence. Subsequently, print statements are integrated to exhibit the structure of the training and testing datasets post the application of the split data function. Verifying the data's structure is crucial to confirm that the division is accurate and aligns with the anticipated layout for training a machine learning model. By dividing the data into input sequences and target values, this code configures the data in a manner conducive to training a forecasting model like a recurrent neural network RNN or a long short-term memory LSTM model, geared towards predicting forthcoming stock prices based on historical data. In the provided snippet, the NumPy arrays heattrain, ctest, heattrain, heatest undergo conversion into PTorch tensor objects. Check out what goes down in the code to kick things off. Essential modules like torch and torch NN are imported. Next up, the NumPy arrays heattrain, ctest, heattrain, heatest get transformed into PTorch tensor objects by leveraging the torch from NumPy method. The resulting tensor's type is explicitly defined as torch tensor through the type method. The conversion of NumPy arrays to PTorch tensors is a crucial step in PTorch operations. It facilitates the smooth melding of NumPy data with PTorch's infrastructure for constructing and training neural networks. This transition ensures that the data flows seamlessly through PTorch's computational graph during both training and evaluation processes. Below is a code snippet that sets up variables with predefined values essential for configuring a neural network model. Set inputDim to 1, which indicates the number of input features. Set hiddenDim to 32. Representing the units per hidden layer of the neural network. Assign num layers as 2 to indicate the total number of hidden layers. Define outputDim as 1, representing the output neurons in the neural network. Specify numipos as 105 for training the neural network model over a set number of epochs. These variables play a critical role in establishing the architecture and training parameters of the neural network. InputDim, hiddenDim, numlayers, and outputDim values dictate the neural network structure, while numipos controls the training iterations on the dataset. Setting up these variables correctly is crucial in developing an effective neural network capable of learning from data and making precise predictions or classifications based on the given task. The following script outlines the implementation of a bespoke GRU-gated recurrent unit neural network model in PTorch for sequence modeling, a prevalent task in machine learning. Essentially, the code accomplishes the following objectives. 1. Establishes the GRU class, a derivative of NN module. This class contains an definitive function to set the model's parameters and a forward function to steer the model's forward progression. 2. Within the definitive function, the GRU model is set up with specifications for input dimension, hidden dimension, layer count, and output dimension. The GRU layer is initialized with the specified dimensions leveraging NN GRU along with an NN linear layer for generating outputs. 3. In the forward function, responsible for forwarding model operations, an input tensor X is subjected to a GRU layer after initializing the initial hidden state to 0 as zeros. The method proceeds to process the input via the GRU layer, capturing outputs and hidden states at individual time steps. 4. The ultimate hidden state undergoes processing through a linear layer to derive the final output of the model. This output materializes as the consequence of the linear player's action on the hidden state from the last time step. This code snippet enables the creation of a tailored GRU model with predefined parameters for tasks like sequence prediction, natural language processing, and time series forecasting. Crafting a custom GRU model empowers us to finely tune the architecture and hyperparameters of the neural network, granting us the flexibility to adapt it precisely to distinct tasks and datasets. The purpose of the following code snippet is to establish and configure a neural network model tailored for sequence prediction. Each line serves a specific function within this setup. To begin, an instance of a gated recurrent unit GRU neural network model is created using the following line: Python model GRU input hidden dim output dim num layers. This step initializes a GRU model with predetermined specifications for input, hidden state, output, and layer count. Next, a mean squared error loss function class is defined to gauge the disparity between predicted and target outputs during training. Python criterion torch class reduction mean. Lastly, the atom optimizer is set up to regulate the adjustment of neural network weights throughout training by utilizing the computed loss to refine the model. Python optimizer torch optim adamidel parameters were 0, 1. By configuring these aspects, the neural network model, loss computation, and optimizer prior to training on a dataset, we lay a solid groundwork for an efficient training process. This preparation helps fine-tune model parameters and enhance performance on the task at hand by minimizing loss. The provided code snippet showcases a fundamental PTorch implementation for training a neural network. Here's a breakdown of its functionality. 1. It commences by setting up an array called chist to hold the loss at each epoch and logging the current time before initiating the training. 2. Within a loop that iterates for a specified number of epochs, the following steps are executed: forwarding the training input data train through the model to generate the predicted outputs trained, computing the loss between the predicted outputs and the actual values trained GRU using a designated loss function referred to as criterion, displaying the epoch number along with the mean squared error maze loss value, saving the loss value in the chest array for the current epoch. 3. Proceeding further, it resets the gradients of all optimized torch tensor variables to 0 via optimizer. 0 grad conducts backpropagation on the loss with loss backward and adjusts the model parameters by invoking optimizer. Step 4. Upon completion of the training loop, it determines the total training duration by calculating the difference between the initial time and the current time, subsequently displaying the training time. This code snippet holds significance as it elucidates the fundamental stages essential for training a neural network using PTorch, which encompass the forward pass, loss computation, backpropagation, and parameter refinement. Through multiple epochs of iteration, the model incrementally reduces the loss function to enhance its performance on the training set. The recording of training time serves as a metric for evaluating the effectiveness and efficiency of the training process. This code fragment appears to be a component of a machine learning endeavor, possibly concerning a recurrent neural network RNN or a comparable model. Essentially, the function sailor inverse transform is applied to revert the alterations carried out by the sailor on both the model predictions trained and the initial data trained GRU. This procedure, termed inverse transformation, essentially restores the scaled values to their primary scale. In detail, trained comprises the forecasted values from the model, while trained GRU embodies the authentic ground truth values pivotal for the model's training. Through the employment of sailor inverse transform, the script translates the scaled forecasts and initial values back to their original scales, rendering them more intelligible and adaptable for assessment or subsequent scrutiny. The outcomes are conserved in data frames predict and original, respectively, for streamlined access and handling. In essence, scaling proves to be a routine preparatory phase in machine learning to standardize the data and enhance training efficiency. Nevertheless, for the conclusive predictions and assessment of the model, reversion of the values to their primary scales is indispensable for superior comprehension and scrutiny. This script snippet accomplishes this by diametrically converting the scaled values back to their original scales utilizing the identical sailor initially employed during preprocessing. In this snippet of code, the Seaborn library is employed to tailor the visualization style and craft a subplot featuring two graphs to exhibit stock price prediction outcomes. To kick things off, the line sans set style dark grid is utilized to establish a plot style exhibiting a dark grid background. Leveraging Seaborn's functionalities, the procedure initiates with the creation of a figure object through pult figure, which is then fine-tuned by adjusting the spacing between the subplots. Setting the horizontal and vertical space with fig subplots adjust space row 2 space row 2. On the left side, subplot 2 line plots are fashioned using sans line plot to showcase both the original data and the forecasted data GRU model prediction. The title, x-axis label, and y-axis label are defined using x set title, x set equable, and x set label correspondingly. To eradicate the x-axis tick labels, x set x tick labels sizenton is employed. On the right side subplot, a line plot is crafted via sans line plot to exhibit the training loss history, analogous to the first subplot. The x-axis label, y-axis label, and title are established to put the finishing touches. The dimensions of the figure are adjusted with fig set phi 86 and fig set fig width 16 to ascertain the height and width are set appropriately. This coding endeavor is essential for visually representing the stock price prediction outcomes and training loss history with a distinctive style and layout to enhance data visualization and comprehension. The customization choices offered by Seaborn, combined with the subplotting technique, play a pivotal role in presenting data in a lucid and enlightening manner. The provided code excerpt plays a critical role in a machine learning initiative or model assessment procedure. Here's a breakdown of the code's functionality and its significance in the context of machine learning. To begin, the code initiates by importing essential libraries such as math, time, and sklearn. These libraries aid in executing mathematical operations, time-related functions, and machine learning metrics correspondingly. Subsequently, it proceeds to predict the output values y by leveraging a trained model using the input data denoted by hottest. Post that, it reverses the predicted values upward to their original state through the usage of a sailor. Likewise, it reverts the actual values y back to their original format. The code further proceeds to compute the root mean squared errors for both the training and testing datasets by employing the mean squared error function sorted from sklearn metrics. The calculated error scores for both datasets are then computed and exhibited. Lastly, the training rooms, testing rooms, and other pertinent metrics are archived for subsequent examination and comparison. The significance of this code lies in its functionality to assess a machine learning model's performance by contrasting the projected values with the true values. Notably, ERMS serves as a widely used metric for gauging the average magnitude of errors in predictions. Through the computation and comparison of ERMS values for both training and testing datasets, it becomes feasible to evaluate the model's efficacy on unfamiliar data and pinpoint any instances of overfitting or underfitting. The storage of ERMS values and associated metrics enables in-depth analysis and comparison across diverse models or hyperparameters, enabling the selection of the most effective model tailored to the specific dataset under evaluation. The code snippet appears to be geared towards time series analysis and forecasting. Let's delve into what each segment of the code accomplishes. First off, the train predict plot function sets up an empty array mirroring the shape of pre-Amazon, later populated with non-values. This array serves as a canvas for plotting predicted training data. Similar to train predict plot, test predict plot is initialized to match the structure of pre-Amazon, serving as a platform for visualizing predicted test data. The initial prices extracted from pre-Amazon undergo a transformation back to their original form from the scaled values. Courtesy of the sailor inverse transform function, predictions are consolidated by horizontally appending train predict plot, test predict plot, and the original values, effectively amalgamating predictions and original figures into a coherent two array. In the final stages, a data frame named result emerges from this amalgamated array. It is plausible that this data frame encapsulates a graphical representation or facilitates further scrutiny of the initial and forecasted values. This code snippet plays a pivotal role in gauging the efficacy of the model and foreseeing future values within a time series. By graphing the predictions alongside the authentic data, the assessment of the forecasting model's accuracy and reliability is considerably facilitated. The script is designed to create an interactive plot illustrating Amazon stock prices over time, depicting train and test predictions alongside actual values using the Plotly library for visualization. Firstly, a fresh figure object is initiated through Plotly's GraphObjects module. Next, 3 traces are incorporated, one for train predictions, one representing test predictions, and the last one displaying actual values, all showcased as scatter plots. To enhance the plot's aesthetics, the layout is fine-tuned to adjust axis visibility, grid lines, and legend display. The x-axis is concealed while the y-axis styling and title are personalized, with a sleek dark theme chosen for the plot's appearance. Furthermore, annotations like the Amazon stock prediction title are integrated into the visual to provide context. This tool is vital for evaluating model accuracy, aiding in decision-making processes based on predictive insights. Leveraging interactive plots enhances data exploration and comprehension, empowering users to delve deeper into the information presented with ease. In this script, the close column is being extracted from a data frame named data and saved into a fresh data frame named pre-Google. Subsequently, the info function is invoked on the pre-Google data frame to present details about it, such as column data types and non-null values. This snippet comes in handy when focusing on a particular data frame column for data manipulation. The info function delivers an overview of the data frame, aiding in grasping the data organization and pinpointing any absent values or necessary data type adjustments for subsequent analysis. This script employs min-max scaling to normalize the close price data of Google stock, adjusting the data to a specific range. To elaborate, min-max scaler is the go-to for scaling features within a set minimum and maximum range, often defaulting to a range such as 1 and 1. Here, the aim is to squeeze the close price data of Google stock into a 1-to-1 range. This procedure proves handy in machine learning scenarios, ensuring all features share a consistent scale and averting scenarios where certain features hold undue sway over the learning process due to their larger magnitude. The fit transform function not only tailors the scaler to the data pinpointing the minimum and maximum values for normalization, but also adjusts the data accordingly with this scale. To comply with min-max scaler's requirements, the reshape 1 operation refashions the data into a singular column if previously multifaceted. In this code snippet, a variable named lookback is initialized to a value of 20, specifying the length of the sequence in a time series forecasting setup. Following that, a function split data is invoked with pre-Google as one of the arguments, presumed to hold historical price data of Google stock or a similar time series information. Alongside lookback, this function partitions the data into input features cuTrain and cuTest and target labels uTrain and uTest based on the designated sequence length lookback. Subsequently, the dimensions of the training and testing data arrays are displayed to confirm the data structure, a common step in ensuring the data is correctly formatted before inputting it into a machine learning system. Utilizing this code segment is crucial for adequately preparing time series information for model training. Restructuring the data sequences into the required input-output setup essential for forecasting model training. Moreover, inspecting the data array shapes guarantees the accurate division of data and its readiness for subsequent processing within the machine learning workflow. This snippet of code serves to convert NumPy arrays, specifically heatmaps, xtest, eTrain, and test into ptorch tensors by utilizing the torch from NumPy function. This conversion is essential to align the data structures with ptorch requirements. Whether you're aiming for optimal performance on a GPU or CPU, the rationale behind this conversion lies in the fact that ptorch is finely tuned for tensor operations, particularly catering to GPU acceleration for swifter calculations. By transitioning the NumPy arrays into ptorch tensors, we unlock the benefits of ptorch's automatic differentiation features and harness the power of GPU processing. To sum up, this code snippet streamlines the process of converting NumPy arrays into ptorch tensors, tapping into ptorch's advanced capabilities, especially beneficial for complex deep learning assignments involving neural networks demanding efficient processing on hardware accelerators such as GPUs. The below code excerpt establishes a neural network model utilizing the GRU-gated recurrent unit design. Here's the breakdown of each instruction. The line model GRU input dim, hidden dim, output dim, numlayers kicks off a GRU model configuration, specifying input dimension, hidden dimension, output dimension, and layer count. Criterion torch. Misclassification mean crafts a mean squared error loss object for evaluating the disparity between the model's forecasts and the genuine values. Optimizer torch, Optim, Adamodel, parameters, Rizero. 1 establishes the atom optimizer that will adjust the model parameters using computed gradients in backpropagation, with the learning rate set at 0, 1. The rationale behind employing this code's initializing the model. Loss function and optimizer are fundamental stages in constructing and training a neural network. The model embodies the structure with adaptable parameters, the loss function gauges the model's performance, and the optimizer refines the model's parameters to minimize losses through training. Uniting these elements constructs a comprehensive framework for training a GRU model for distinct assignments like sequence forecasting or time series predictions, empowering the model to recognize patterns in input data and generate precise forecasts. Below is a rundown of a p-torch training loop meant for a neural network model that showcases various functionalities to kick things off. 1. An array named chest is initialized with 0 serving as storage for the loss values across epochs. 2. Time kicks off with the start of a timer to track the duration of the training. 3. The list GRU is initiated blankly to accommodate upcoming elements. 4. The loop runs through each epoch ranging from 0 to num epochs. 5. The neural network model carries out predictions on training input data trained to derive utrain pred. 6. Determining loss involves comparing utrain pred with the actual utrain GRU utilizing a specified criterion for loss function. 7. Each epoch number and the mean squared error maze loss value are showcased. 8. The loss value is then stashed in the chest array at the current epoch. 9. Resetting the optimizer's gradients happens with optimizer 0 grad. 10. Through backpropagation loss. Backward, the gradients of the loss regarding the model parameters are computed. 11. The model parameters refresh based on the calculated gradients through the optimizer. Step 12. Upon wrapping up all epochs, the total training time computes, obtained by subtracting the initial time from the current time and then divulged. This code play-by-play is pivotal when it comes to nurturing a neural network model via supervised learning using p-torch. Allowing the model to grasp insights from the training data, it strategically updates its parameters, progressively reducing the loss function to uplift its predictive prowess. Through the training loop, the model meticulously fine-tunes its weights during multiple iterations epochs until it eventually gravitates towards a parameter set culminating in minimal training loss. The provided code snippet reverses the scaling transformation applied to the predicted and original data using a sailor. Below is a breakdown of each segment of the code. 1. Undoing the scaling that was previously applied to the data is achieved through the function sailor. Inverse transform. Scaling data within a specific range before model training is a common practice in various machine learning scenarios aimed at enhancing model efficiency. 2. For the predicted data, the code snippet utrainpred, detach. NumPy first isolates the predicted values from the computational graph, typically in frameworks like p-torch. This is followed by converting the values into a NumPy array to facilitate the subsequent application of the inverse transformation using the designated sailor. 3. Taken to the process described above, utrain GRU. Detach. NumPy serves the purpose of disengaging the original data from the computational graph and transforming it into a NumPy array to ready it for the inverse transformation. 4. The resultant transformed predicted and original data are then housed in Pandas data frames named predict and original, respectively. By employing this code, the aim is to juxtapose the model's predicted values, generated through a neural network utilizing GRU, with the genuine ground truth values. By reverting the previously carried out data scaling, the values are restored to their original scale, enabling a meaningful assessment and performance evaluation of the model. In this Python snippet, Seaborn and Matplotlib libraries are utilized to craft a visual depiction of data. The rundown of the code's functionality is as follows. 1. It configures Seaborn plot style to dark grid for a specialized aesthetic. 2. A figure is initiated through pult figure to encompass the subplots. 3. Modification of spacing among subplots is done via fig subplots adused, managing both horizontal and vertical spacing. 4. The initialization of the first subplot 1. 2. 1 entails the usage of sins line plot to exhibit two line graphs on a shared axis, configuration of title axis label, the axis label, and concealment of axis tick labels. 5. Preparation of the second subplot 1. 2 includes deployment of a line plot through SINs. Line plot with data stored from the GIST dataset. Specification of axis label, axis label, and title for the second subplot. 6. The final touches involve setting up the figure's dimensions with fig. Set phi height and fig, set fig width. This script proves handy for juxtaposing two line plots side by side, such as displaying stock price data alongside training loss data for comparative analysis. Leveraging Seaborn and Matplotlib libraries allows for ample customization of the visualization's appearance and design. The provided code snippet appears to analyze the effectiveness of a machine learning model in regression tasks by utilizing root mean squared errors as an evaluation metric. The breakdown of the code operation is as follows. Initially, essential libraries are imported, like math for mathematical computations and time for time monitoring purposes. Then, it fetches the predictions generated by the model stored in utestpred for the test dataset test. The code proceeds to reverse any normalization or scaling applied during training by performing an inverse transformation on both the forecasted and actual values for the training and test sets. Employing a scalar object, subsequently, it computes the rooms between the predicted and actual values for the training set utrainpred versus train and the test set utestpred versus test utilizing the mean squared error function within the Sclearn metrics module. The RMS results for the training and test datasets are then displayed. Finally, the calculated RMS values for both the training and testing datasets, accompanied by the training duration or added to a container named GRU. Presumably, the GRU list is utilized to retain these metrics for monitoring and further analysis purposes. Evaluating a regression model's performance is crucial, where RMS serves as a widely accepted measure for evaluating the accuracy of predictions made by regression models. By comparing RMS scores across the training and test datasets, one can infer the model's generalization capability and identify potential cover-fitting concerns. Compiling these assessments in a list such as GRU facilitates comparisons between various models, hyperparameter adjustments, and ongoing performance tracking. The provided code snippet appears to be a vital component of a machine learning or time series forecasting endeavor. Let's delve into its functionalities. 1. Initiating train predict plot and test predict plot. These arrays are initialized to mirror the dimensions of the pre-Google variable. They serve as containers for storing the predicted values produced by the model, initially populated with NaN placeholders. 2. Populating train predict plot and test predict plot as the model generates predictions for the training utrainpred and testing utestpred datasets. These forecasts are respectively deposited into train predict plot and test predict plot at their corresponding positions within the arrays. 3. Reversing the transformation. The initial price data, earlier subjected to processing alterations like normalization or scaling, undergoes an inverse transformation to revert back to the original price values. This step is imperative for juxtaposing the model's projections with the genuine prices. 4. Merging forecasts by horizontally concatenating train predict plot, test predict plot, and the authentic data. The composite predictions array is established, likely featuring 3 columns encompassing training forecasts, test predictions, and original prices. 5. Conversion to data frame. Transforming the predictions array into a Pandas data frame dubbed result. This data frame could serve in subsequent analyses, visual representations, or juxtapositions between the anticipated and factual values. This code fragment plays a pivotal role in evaluating the efficacy of a machine learning setup designed for predicting stock prices built on historical data. It aids in visually aligning the model's prognostications with the factual prices to gauge precision and efficiency. Moreover, the data transformation and structuring methodology employed here paves the way for diverse critical analyses and evaluations crucial for appraising the model's effectiveness. In this script snippet, Plotly, a Python graphing tool, is leveraged to craft a visual representation of stock prediction outcomes for Google shares. Below is a breakdown of the methodology. 1. It begins by importing crucial modules from Plotly Express for simple and swift plotting, and graph objects for precise control over the plot's details. 2. A fresh figure instance is spawned to house the visual plot. 3. 3 scatter traces are incorporated into the figure, each symbolizing distinct data series linked to stock forecasts: training prediction, testing prediction, actual value. 4. The figure's layout is modified to tailor the plot's aesthetics, encompassing settings for X and Y axes, titles, axis labels, legend visibility, and the chosen color scheme dark theme in this instance. 5. Annotations are integrated to provide additional context to the plot, such as the header Google stock result placed atop the visualization. 6. Subsequently, the figure is exhibited and presented utilizing Fig Show. Employing this code snippet allows for a lucid and interactive portrayal of the stock prediction findings, aiding in comprehending and scrutinizing the data efficiently. The visualization encompasses both training and testing predictions alongside actual values, facilitating a comparison of the model's effectiveness and the detection of any trends or anomalies. With customization options readily available, tailoring the plot to suit specific requirements and preferences becomes feasible, rendering the data more accessible and captivating for deeper analysis. In the provided script, the close price information is extracted from the datum data frame and stored in a fresh data frame labeled presum. By employing the info method, a comprehensive overview of the presum data frame is presented, highlighting details such as the count of non-null entries and the data types of individual columns. This snippet proves handy for a swift review of the structure and essential details concerning the isolated closed prices from the datum data frame. It serves as a reliable checkpoint to confirm the accurate extraction and alignment of the data prior to any subsequent analysis or manipulation. Utilizing the min-max seller from the scikit-learn library, this code snippet normalizes the close prices of head stock. Normalization is crucial in scaling numeric values to a defined range, generally between 0 and 1 or 1 and 1. It aims to standardize features to ensure even weighting in machine learning algorithms. Within this code snippet 1, an instance of min-max seller is instantiated, specifying a feature range of 1 to 1. 2. The closed prices of hidden stock are reshaped into a two-dimensional array, then fed into the fit transform method for normalization. 3. The closed prices get updated with the normalized values in the presum dataset. This coding process is vital to guarantee that closed prices maintain a consistent scale, preventing them from overshadowing other attributes in machine learning algorithms that depend on proximity measurements. Normalization plays a key role in stabilizing and refining model performance by aligning all features to a comparable scale. In this script, a variable named lookback is established with a value of 20, signaling the required sequence length. Following that, the split data function is invoked with presum data and the lookback parameter. This function is expected to segment the data into input features and labels necessary for training and evaluating a machine learning model successfully. The output statements exhibit the shapes of who-train, who-test, u-train, and u-test to provide insight into the dimensions of the training and testing data. Grasping these shapes is fundamental to validate that the data is being manipulated accurately and aligns with the anticipated format for training a model effectively. To sum up, this code snippet is laying the groundwork for training a machine learning model by fragmenting the data into sequences of a designated length dictated by the lookback value, a crucial step for enabling time series or sequence-based models to discern patterns from historical data. This piece of code begins by importing the PTorch library and its neural network module. Afterward, it transforms the NumPy arrays cutrain, custest, atrain, and dotest into PTorch tensors utilizing torch. From NumPy, this conversion is crucial when dealing with neural networks developed in PTorch, as it equips the tensors with Kabu acceleration for faster computations, facilitates automatic differentiation for gradient computations in neural networks, and ensures compatibility with PTorch's neural network modules. This data conversion to PTorch tensors enables smooth integration with PTorch's deep learning capabilities. The following code snippet is designed to set initial values for variables crucial in defining a deep learning model. The inputDim parameter denotes the dimensionality of input data. HiddenDim specifies the number of neurons in each hidden layer. NumLayers indicates the total hidden layers in the neural network. OutputDim represents the dimensionality of the output data, and NumIpos determines the number of iterations the model will undergo in training. These values are pivotal in shaping both the structure and functionality of the deep learning model. For instance, HiddenDim and NumLayers directly impact the model's ability to grasp intricate patterns within the dataset, while InputDim and OutputDim dictate the configuration of the input and output layers, respectively. Precisely configuring these variables is fundamental in constructing a powerful and efficient neural network model capable of generalizing effectively to unfamiliar data. By establishing these values at the outset, developers can customize the model's structure to align with the specific demands of the task at hand and streamline the training process for enhanced performance. Within the context of configuring a neural network model for training with the PTorch library, the following details are inherent in coding the specified input dimensions, hidden dimensions, output dimensions, and number of layers initializes the GRU model within the neural network. A variant of CRNs known as gated recurrent unit, MSCLUS, an abbreviation for mean squared error loss, serves as a prevalent loss function tailored for regression scenarios where the objective is to minimize the average squared variance between the anticipated and factual target values. ATOM, an optimization algorithm expanding on stochastic gradient descent, is renowned for its efficacy in the realm of training deep learning models. In this particular instance, the initialization of the ATOM optimizer facilitates the adjustment of model weights throughout training via the stipulated learning rate. This method of configuring the model, specifying the loss function, and defining the optimizer erects the foundation for the forthcoming training endeavor of a neural network model utilizing the GRU framework coupled with mean squared error loss and a reputable ATOM optimizer. Such an arrangement mirrors a conventional approach in deep learning for outlining model architecture, streamlining the training procedure, and laying out the optimization strategy. In this code snippet, you can observe a training loop for a neural network model utilizing PTorch. Let's break down its functionality. 1. An initial step sets up a NumPy array named chis to record losses per epoch and kicks off a timer to monitor training duration. 2. An empty list GRU is prepared. 3. The code then proceeds through a set number of epochs. A. Predictions you trained or made using the neural network model on the training data train. B. Loss is computed by comparing the predicted values you trained against the actual values you trained GRU. C. Epoch number and mean squared error mace loss are printed for tracking purposes. D. The loss value is stored in the chist array. E. Backpropagation is carried out by resetting gradients, calculating loss gradients concerning model parameters, and adjusting weights with the chosen optimizer. 4. Upon completion of all epochs, the total training time is calculated and displayed. This code snippet is vital for training a neural network model. Throughout training, the model endeavors to minimize the loss function, which gauges the disparity between predicted and target values. By iteratively updating the model's weights via gradient descent, its performance on the assigned task enhances. The training loop streamlines the process of tuning the model's parameters for improved predictions on training data. The printed loss values furnish insights into the progress and efficacy of the training regimen. Lastly, tracking training duration aids in assessing the efficiency of the training process. A snippet of this code includes utilizing the inverse transform function of the Saylor object to reverse the scaling applied to the anticipated and initial datasets for comparison or subsequent analysis. The tensors trained and trained GRU in this code stem from a PTorch model. To employ the inverse transform function on these tensors, they must first be transformed into NumPy arrays utilizing detach NumPys. Subsequently, the Saylor inverse transform function is employed to convert the normalized predictions and original values back to their initial scales prior to preprocessing and training. This code segment is crucial because during model training, it is customary to scale the data, such as using minmax Saylor or standard Saylor, to guarantee that the characteristics are within a comparable range. This practice aids the model in quicker convergence and improved performance. Nevertheless, for analytical or comparative purposes, it is vital to reverse the scaled values to their primary scales. The inverse transform function serves this purpose by restoring the values to their original states. The presented code snippet showcases the creation of a visual representation utilizing the Seaborn library within the Python environment. It constructs a figure featuring two subplots positioned side by side. In the initial subplot, it exhibits a line plot juxtaposing actual data original against predicted data with distinctive coloring for each line. Additionally, it configures titles, labels, and tweaks various visual elements of the plot. The subsequent subplot illustrates a line plot of training loss values extracted from the hist variable. Similar to its predecessor, it refines the plot's appearance by incorporating suitable labels, titles, and color schemes. By invoking the license set style dark grid, the code establishes a dark grid background as the visual theme for Seaborn plots. This choice aims to elevate the readability and aesthetic charm of the plot. This code bears significance as visualizations serve as pivotal assets in the realm of data analysis and comprehension. Through the utilization of libraries like Seaborn, individuals can generate visually engaging and informative plots that aid in data comprehension, pattern recognition, and effective communication of outcomes to diverse audiences. Furthermore, the array of customization tools afforded by Seaborn empowers users to tailor plots according to specific requirements and preferences. In this code snippet, the model generates predictions denoted as UTestPred based on the input test data HTest. The predicted values are then converted back to their initial scale using Sailor. Inverse transform for both the training and test data predictions UTrainPred and UTestPred. Correspondingly, the actual values UTrain and UTest are also reversed to allow for a comparison. These actual values represent the target outcomes that the model aims to foresee. To assess the model's effectiveness, the root mean squared error RMS is computed for both the training and test sets as a metric. RMS serves as a gauge of the disparities between predicted values by the model and the factual values. Smaller RMS values suggest a superior performance of the model. Subsequently, the RMS scores for both sets are displayed on the console. Next, the training RMS, testing RMS, and training duration are saved in an array or list named GRU. This practice aids in monitoring the model's performance across various iterations or diverse models. Overall, this code segment gauges a machine learning model's efficiency by determining RMS for the training and test sets, reveals the scores, and retains them for further scrutiny to revert the normalized predictions to their original scale for comparison. Sailor inverse transform is employed. The mean squared error function from the Sclaren metrics module is leveraged to compute the RMS. This code snippet appears to be connected to a machine learning algorithm for forecasting stock prices. Here's a breakdown of its functionalities. The first step is to set up two arrays, train predict plot and test predict plot, to match the shape of the presim array and then assign null and values to them. Next, it fills train predict plot with predictions based on the training data UTrainPred generated by the model. Simultaneously, test predict plot gets populated with predictions on the test data UTestPred. To revert the scaled stock prices to their original form, the code utilizes an inverse transformation method Sailor. Inverse transform as the model was trained on scaled data. Subsequently, it merges the train predict plot, test predict plot, and the original stock prices arrays into a combined array named predictions. Finally, a Pandas data frame labeled result is constructed using the integrated data from predictions. The primary objective of this code is to juxtapose the original data with the predictions produced by the machine learning model concerning both training and testing datasets. This comparison aids in assessing the model's efficacy in predicting stock prices and provides a visual representation of how well the model corresponds with the factual data. By portraying this information within a data frame, one can scrutinize and interpret the discrepancies and trends between the real stock prices and the forecasted values. The following script employs Plotly to render a visualization of item stock prediction details. Initially, it establishes a figure entity encapsulating various traces for train prediction, test prediction, and actual value through scatter plots. Subsequently, it tailors the plot layout by specifying properties for the x-axis and y-axis, such as color schemes, font selections, and tick arrangements. Additionally, it incorporates a plot title and switches the template to a dark theme to enhance clarity. Post setting up the plot layout, it inserts an annotation onto the plot bearing the text item stock prediction at a designated location within the plot. Ultimately, invoking Fig showcases the plot encompassing the refined data and layout configurations determined earlier. This piece of code proves valuable for visually interpreting and scrutinizing stock prediction data, ensuring an easier grasp of underlying trends and patterns within the dataset. Extracting the close prices of Microsoft stock from the Microsoft data frame and saving them in a separate data frame named pre-Microsoft can be accomplished with the following code snippet. Subsequently, by employing the info method on the pre-Microsoft data frame, you can access a comprehensive overview of its characteristics. encompassing the data types of each column, the entry count, and memory allocation. Utilizing the info method proves invaluable in comprehending the composition of a data frame thoroughly. Covering aspects like its dimensions, data types, and memory utilization, this insight proves pivotal in tasks such as data interpretation, quality enhancement, and memory management, aiding users in making well-informed choices regarding proficient data manipulation and analysis. In this code snippet, the min-max scaler from the scikit-learn library is employed to adjust the close prices of Microsoft stock to a predetermined range of 1 to 1. Let's delve into the breakdown of the code functionality and its significance. 1. Importing min-max scaler. Initially, the code imports the min-max scaler class from the scikit-learn library. This class enables the scaling of numerical features to a specific range. In this scenario, from 1 to 1, 2, by instantiating a min-max scaler object next. An object of the min-max scaler class is instantiated while setting the feature range parameter to 1. 1. This setup ensures that the data will be scaled to fit within the 1 to 1 range. 3. Descaling the close prices. The code extracts the close prices of Microsoft stock, reshapes them into a 2D array, and then invokes the fit-transform method of the min-max scaler object with the close prices as input. Through this method, the scaling transformation is applied to the close prices, and the scaled values are reassigned to the close column. This code snippet serves the purpose of standardizing the close prices of Microsoft stock to a specific range 1 to 1 without distorting the original data differentials. Standardization is crucial in machine learning to ensure that features are within a similar scale, ultimately enhancing the efficacy of certain algorithms and offsetting biases stemming from variations in feature magnitudes. The following script carries out the following operations. 1. It initializes a variable named lookback with a value of 20 to determine the length of the sequence. 2. It invokes the function splitData with pre-Microsoft and lookback as inputs. This function is likely responsible for organizing the training and testing datasets by generating data sequences with the specified length of lookback. 3. The obtained training and testing data are stored in variables htrain, atrain, custest, and heatest. 4. To verify the dimensions of the prepared datasets, the script displays the shapes of the training and testing data arrays. This code is crucial for preparing sequential data to train machine learning models, particularly for tasks such as time series prediction or sequence forecasting where historical context plays a vital role. Segmenting the data into input-output pairs based on a particular lookback value enables the model to discern and capitalize on underlying patterns within the data. Having an understanding of the data structure is essential to ensure its proper formatting for the model training phase. In this script, the PTorch library is being utilized to transform NumPy arrays into PTorch tensors, which are arrays of multiple dimensions utilized for computations on corpus. 1. The function torch from NumPy is employed to generate a PTorch tensor from a NumPy array. 2. To explicitly specify the data type of the tensor as torch. Tensor, the typetorch tensor method is utilized, while usually unnecessary due to PTorch's ability to automatically infer data types. In certain cases, it can be beneficial for maintaining consistency or ensuring compatibility. The conversion of NumPy arrays into PTorch tensors is crucial when dealing with neural networks and deep learning models in PTorch, since PTorch relies on tensors for its calculations, optimizations, and autograd functionalities. By converting data into PTorch tensors, we can leverage PyTorch's features for creating, training, and assessing neural networks. This piece of code sets up the fundamental variables commonly utilized in neural network designs. The input dim signifies the count of features in the incoming data, while hidden dim dictates the quantity of neurons housed within each hidden layer of the neural network. NumLayers, on the other hand, outlines the complete quantity of hidden layers the network encompasses. Following that, outputDim showcases the volume of output units featured in the neural network, a figure contingent upon the task at hand. Lastly, NumIpos portrays the overall number of iterations a training algorithm will undertake across the entire dataset in the training phase. These variables hold pivotal importance in configuring the structure and training regimen of a neural network. By specifying these parameters at the start, we can manage the model's capacity, intricacy, and learning tendencies to enhance its performance based on the specific demands of the given problem. Here is the code snippet for configuring a neural network model using a gated recurrent unit GRU for a specific task. The GRU model is a valuable tool for handling sequential data in neural networks. Let's break down the purpose of each segment in the code. 1. Initializing the GRU model GRU input hidden dim output dim num layers. This part sets up the GRU model with defined parameters like input dimension, hidden dimension, output dimension, and number of layers. This model is essential for processing input data effectively. 2. Setting up the mean squared error maze loss function criterion torch. Class reduction mean by initializing the maze loss function. This code line allows for evaluating the variance between predicted values and actual values, typically used in regression tasks. 3. Configuring the Atom optimizer torch. Adamodel. Parameters 0, 1. Here, the Atom optimizer gets initialized with a learning rate of 0, 1. This optimizer is crucial for adjusting the GRU model's weights through learning, based on the loss computed by the maze loss function. This code snippet is pivotal for establishing a neural network model with the appropriate architecture, loss calculation method, and optimizer for training purposes. Through this setup, the GRU model can efficiently detect patterns and provide accurate predictions on a specific dataset. The provided code snippet outlines a training loop designed for a neural network model, likely a GRU-gated recurrent unit model. Let's break down its functionality. 1. It sets up an array called hist to track losses per epoch, initializes a start time for training, and creates an empty list named GRU. 2. It initiates a loop that lasts for new MIPOS cycles. During each cycle, a predictions you train pred or made using the model on the training data has trained. B. The loss between you train pred and the actual values you train GRU is computed. C. Both the epoch number and the mean squared error maze loss value for that epoch are displayed. D. The loss value is appended to the hist array for monitoring purposes. A. Backpropagation is executed by resetting gradients, computing the gradients of the loss concerning the model parameters, and adjusting the model parameters using the optimizer. 3. Once the training loop concludes, it determines the total training duration by calculating the difference between the start time and the current time, before displaying the training time. In essence, this code plays a pivotal role in training a neural network model by iterating through the dataset numerous times, evaluating losses, and fine-tuning the model parameters to diminish the loss via gradient descent. This process aids in enhancing the model's predictive accuracy on new data. This piece of code specifically handles the conversion of scaled predictions back to their original form along with the original target values. To achieve this, the inverse transformation technique is applied using the Saylor inverse transform method to revert the scaled values to their initial scale. 2. By utilizing the PD data frame function, a Pandas data frame is generated from the transformed NumPy arrays. 3. Before executing the inverse transformation, the prediction and original values are converted to NumPy arrays with utrainpred, detach, NumPy and utrain GRU, detach, NumPy. The purpose of this code is to compare the model's predictions with the genuine target values in their unaltered state. It plays a crucial role in assessing the model's performance, visualizing outcomes, and comprehending how effectively the model can predict target values. This snippet of code utilizes the Seaborn library to create 2 subplots, a tool for visualizing statistical data that builds upon Matplotlib. The initial subplot to the left showcases the real data alongside the predicted values for comparing stock prices through line plots. The subsequent subplot on the right exhibits the training loss across various epochs throughout the training phase. Breakdown of the code's functionalities. 1. Adopts the dark grid style from Seaborn to enhance the aesthetic appeal of the plots. 2. Establishes a figure object to accommodate the subplots and configures the spacing between them. 3. Constructs 2 subplots wherein the first subplot involves dual line plots for juxtaposing actual and predicted stock price data. 4. Defines titles, labels, and formatting specifications for the first subplot, specifically focusing on Microsoft stock price comparison. 5. The second subplot demonstrates a line plot illustrating the training loss evolution across epochs in a model training scenario. 6. Sets titles, labels, and format preferences for the second subplot, primarily centering on training loss. 7. Adjusts the figure's dimensions for improved visibility. This code snippet aids in visualizing and scrutinizing stock price data as well as training loss over epochs, aiding in the identification of trends, patterns, and performance evaluations throughout the machine learning model training and prediction assessment phases. Seaborn Library serves as a sophisticated tool for generating informative and visually appealing statistical graphics. The provided code snippet serves the purpose of assessing the effectiveness of a machine learning model, specifically a GRU-gated recurrent unit model, in a time series forecasting scenario. This is achieved through several steps. To begin with, the code imports essential libraries such as math, time, and mean squared error from scikit-learn. These are utilized for mathematical computations, time monitoring, and calculating the mean squared error. Subsequently, predictions are made on the test dataset UTestPred by employing the trained model on the input test data HUTest. Following prediction generation, the code reverses the scaling transformation previously applied during preprocessing on both the predicted values utrainpred, ITestPred, and the true target values utrain, ITest. This reverts the values back to their original scales for accurate error assessment. The code then proceeds to compute the root mean squared error between the predicted and actual values for the training and test sets by utilizing the mean squared error function. The resulting scores for the training and test sets are subsequently displayed on the console to gauge the model's performance. serves as a widely used evaluation metric for regression models, offering a comprehensive view of the model's error magnitude. Lastly, the code appends the scores for both training and test sets to a list GRU, likely aimed at monitoring the performance metrics across different experiments or models. In essence, this code snippet plays a crucial role in gauging the accuracy of the GRU model for time series prediction tasks. It aids in assessing the model's ability to generalize to new data and provides valuable insights into prediction accuracies. Monitoring scores over varied experiments can guide model selection and fine-tuning of hyperparameters effectively. The provided code excerpt serves a crucial role in visualizing forecasted stock prices produced by a predictive model. Leveraging historical price data to elaborate on the code's functionality initially, the code initializes two arrays, namely train predict plot and test predict plot, with NIP, NaN values to capture and preserve the anticipated results. Subsequently, it appends the predicted values for the training and testing datasets into their respective arrays, reflecting the model's forecasts. Following this, the code reverts the original stock price data to its primary scale through the implementation of the Saylor's inverse transform function. Furthermore, it consolidates all forecasted and original values into a unified NumPy array, termed predictions, facilitating subsequent plotting and visualization tasks. Lastly, the amalgamated predictions array is transformed into a data frame labeled result, empowering further examination and visualization endeavors. This code segment proves essential in assessing the predictive model's efficacy by contrasting projected stock prices against factual historical stock values. Visualization aids in gauging the model's efficiency and pinpointing any disparities between anticipated and real values, assisting in making sound decisions concerning trading or investment strategies. Utilizing the Plotly Python library, this script generates an interactive graph showcasing forecasts for a stock market dataset. Here's a breakdown of its functions. 1. It starts by importing essential modules from Plotly, Expression Plotly, Graph Go. 2. An initial figure is instantiated using toGo figure. 3. Subsequently, 3 traces are included in the figure via fig. Add trace, each representing a distinct line plot pertaining to various data points within the result data frame. 4. The plot layout is customized through fig. Update layout to tweak details on the coaxis and y-axis appearance, such as line color, grid visibility, and tick labels. 5. A legend is incorporated into the plot to distinguish between train prediction, test prediction, and actual value. 6. The plot adopts the Plotly dark template to provide a dark theme. 7. An annotation is placed at the top left corner of the plot, labeling it as Microsoft Stock Prediction. 8. To visualize the graph, fig show is executed. This code effectively visualizes and assesses stock market prediction outcomes, facilitating data interpretation and trend identification. Plotly's interactive functionalities enable users to delve deeper into data analysis by zooming, panning, and exploring data points on the plot.